10th, and today is August 7th.
Yeah.
And my internship start time is to now is 2 months. So this will be my last talk in here, and I'll be leaving Taiwan next week. So today will be the last day in Sinica. I'm going to give the summer reports on what I've been doing for over the 2 months. I don't want to focus too specific on the project that I'm working on, but it's a broader overview of what I'm doing. And then later I will talk about something that I'm working on recently, and something that I actually just finished some data analyzed yesterday. And so basically this report is to kind of give you guys an overview of what I'm doing and to showcase my research ability. Okay, so pretty simple. I want to start with what is dark matter, what are gravitational waves, and what is LIGO interferometer. So I'm going to start with dark matter. So before I came here, I had zero understanding of dark matter. I don't know much about the dark matter and what that is, and I think a lot of people also have that kind of questions. But later on, I figured out that dark matter is actually particles, or some kinds of matter that's yet defined, which is meaning, in other words, is actually that we still don't know what that is. And there are some particles that we already know, but dark matter is actually a broader term for those particles that we yet define, and those particles or matters that we try and define. And so dark matter is actually make up all the about like 20 or 30% of the universe, and the other percentage of around like 60 or 70% are dark energy. And these kinds of matters actually made up 95% of the whole universe. So what we see right now, the visible particles and those the things are actually only containing 5% of the total universe masses. And so the dark matter is actually quite a lot, actually much larger than the 5% that we can see in this physical world. And so dark matter is basically something that we yet define, and we are trying to figure out right now. And then I think it's very important to talk about the gravitational waves, because gravitational waves actually relate to dark matters. And gravitational waves is actually something that we're working on over the past two months. And so the gravitational wave is actually simply describing the waves that is being generated, or the signal that is being generated by those dark matter. And as we know, the dark matters have masses, and the masses, based on the Einstein's relativity, every mass is propagated, or like there's a signal propagated in the Ripple space-time. And so every mass will essentially have gravitational wave, and it kind of just producing the gravitational wave. So you can actually imagine that the gravitational wave is actually related to the gravity. Every mass, every object that has masses will generate a gravitational wave, and so it propagated into a gravitational wave. And so essentially, that by knowing that there's a gravitational wave signal, that we can predict that there might be masses that kinds of it can be a dark matter, it can be a dark energy. But by using the gravitational wave, we can know, okay, there might be a dark matter or a dark energy, because we don't know what that is. Only by using gravitational wave, a source that's tracing back to the dark matter. Okay, there might be a typo. This should be an interferometer. But basically, interferometer is an interference instrument that are actually detecting how gravitational wave affecting object. And so the funny thing about the gravitational wave is actually when the object being hit by the gravitational wave, it will shrink, it will stretch, it will compress. So, but that kind of scope is very, very small. It's very narrow. But interferometer is so sensitive that it actually measuring the distance change and also the mirror is being compressed or stretched, and then it will change the refracted index, and so and also changing the distance in between the mirrors. So the interferometer actually detecting the changing distance between the mirror, and then allowing us to know whether there's a gravitational wave signal.
Sorry,
Yes.
I have a question.
Yes.
Can I say that when the gravitational wave comes,
Right.
not just the length of the arm changes, but the wavelength of the laser also changes. So basically, nothing changes for this system. Can I say that?
Nothing changed for the system. You mean the wavelength also changed?
Also changes, and the arm length, the length of the arm also changes. So for this instrument, nothing changes.
Mm-hmm.
So basically, we cannot detect anything. Can I say that?
I think we cannot say that. I think so.
Yeah.
Because I think we have to consider, so the signal is actually hitting the interferometer, right? And so as you say, it can change you mean the wavelength, so that's meaning the signals also change. So that's meaning the distance between that is also changed, so that we cannot detect whether the signal is dark matter or is a gravitational wave or not. But I think when we consider the signal, we have to also consider the noise. And so I think as we going farther, we actually wanted to figure out that actually there is a signal and a noise ratio. So I think if you say that also the wavelengths also change, then we can see that there is a signal and noise ratio will be also changing. So I think I think when the gravitational wave hit the interferometer, it will definitely change the ratio. But you know, sometimes maybe it's hard to define whether that's a gravitational wave or not, because you say the distance and also the wavelengths are both changing. But we can see that the ratio is changing, and we can say, okay, maybe there might be a gravitational wave. That's my thinking, but maybe that's a. Thank you so much for the question.
Yes, maybe not. So,
Right.
so A, we do see gravitational wave. So something must be detectable. I think that the wavelength remains, but then the correct language is that space-times
The space-time. Right.
wobble.
Right.
Sometimes some people use wobble if they use change. And then they say, and this wobbling, this change is coherent. Has correlated in two directions.
Right.
So one strengthens and then one extends a little bit, and this gives the signal. And it's not, the gravitational waves, it's not hitting, it goes through the whole space, changing the local space-time structure.
Right.
So it's not really in our language of hitting it.
Oh,
It's just because when we have a mass, we distort the space-time.
Right.
So we know that the mass and the space-time is not totally flat. It's related.
Right.
Yes. So this is a dynamic version of the static situation. Yes. So this is how most people would understand. And at the end, it's a data science, so we do see no way. And we see it in the state of Washington and in the state of Louisiana in coincidence. At the same funny shape.
Right.
So this is hardly difficult to call it just random noise.
Right.
So this is how I think most people would understand it.
Okay. And when we get into, so once we're using interferometer to receive the signal of gravitational wave, we have to do some process to be able to analyze those signals. And so I think there's three very important components or mathematical definitions of how we are getting those signals and then turn those signals in the way that we can analyze. So that will be, there are three key mathematical definitions: cross-correlation, convolution, and match filtering. And so I think this is more a mathematical description of these, I guess, questions. But the simple understanding of match filter and cross-correlation or even convolution are just simply, imagine there's two images, and then there's two images, and one is part of the bigger image, and you want to see how much they match each other. And so that's essentially just match filtering. You see two signals, how in line they are with each other. And so that's basically the definition of match filtering. So so this is actually applying to when we analyzing the noise and the signal, how much they match each other, and also the templates that we insert into match filtering. And so when we have our own generated templates, and we also have the templates, or in other words, a signal from the LIGO raw data. And we want to comparing the inserting templates in the raw data using match filter. And so so match filter and cross correlation, these are simply quite similar terms. But essentially, we are analyzing these signals using match filter as our main focus. So we can see that we're inputting the signal, and then match filter is actually helping us return the signal to a more specific area. So we can actually amplify the signal that match the expected pattern. Okay, so now that's a broader overview of what I'm doing. I want to focus on something that I'm working on the past week. It's actually identifying coordinates. The third hole where match filter discriminates the power. And the second one is determining the beam size at which the SNR drop campus at the reference value. And so what I wanted to do this is actually just wanted to know the sensitivity of the match filter, the sensitivity of the match filter, because we assume that there might be a limitation of the match filter that we can distinguish whether this signal is signal or is noise, or we can, in other words, whether we can comparing the inserting templates or with the raw data from LIGO. So right now, so the past 2 weeks actually working on this, but until this past week I kind of find the critical range of where match filter started to lose its sensitivity. And so right now my method is actually finding to changing the coordinates, of the scanning range. So I'm going this directions, and I modify the scanning range using an interval from 100 to 10 to the -60. And so that will be the beam size. That will be the beam size. And then I want to observe how SNR values their different coordinates. And so this is actually, I did it last week, but this week I'm actually working on more, I have a little more programs. So, and I want to explain before I jump into, I need to have a reference points, coordinates, and I need to also to compare it. So I'm using reference points as a foundation, and then I have other coordinates to compare with that reference points. So the reference point has its own templates, and I'm using these templates to compare other coordinates templates. And so I start with 3,800, and why I want to start with that point is actually suggested by Team E. And that actually around like a 3,800 is actually the impulse of the signals. And so that on this part, that actually if I'm starting at that point, actually I have more, I can easily more easy to see there is a signal or there is more higher impulse in there, so that I can be easy to analyze the signal. So I start with the beam size from 100, we see that there's a pattern until here. It seems that the match filter no longer can distinguish between the inserting templates and the raw data. So we can see if we going down here, we can see after that after that it's no longer loses the sensitivity. But in between, so I figure out in between here, in between these two range, these two, I guess, band size is actually the critical range. So I think this is something that I figured out. And so this is actually the results I find. These are the data, the critical range. We can see that the SNR here is actually jumping around. It's not increment with the constant increments, but actually jumping around. Sometimes increasing, sometimes decreasing, sometimes constant. But before that, before 10 to the negative 9.5, everything is, we are able to distinguish between the inserting templates and the raw templates. Okay. And then I also do a little research on the beam size, 10% decay of SNR. And then I choose to fix the sample rates at 4,096. And then I decreasing around 92, 93. And then that will be the 93 will be the beam size. And then we can see that the decrease is 10%. But later on, if I continue to decreasing the coordinates, actually the SNR is decreasing more rapidly. So I think I have to continue to do more research on this. It seems that there is a 10% drop from here to here. So that will be 10% drop. All right, and so the conclusion is the match filter reaches sensitivity limit when the scan interval falls between 1 to the negative 9.5 and 1 to the negative 10.25. And then as shown in plot 1 and table 1 here, the SNR dropped from this to this, which is the reductions of roughly 10%. And then the coordinate changed from, so it's changed to 90. So that would be the decay of 10% of SNR. So I think I wanted to start a little bit before I finish this talk, is that we may encounter calculation limitation due to the constraints of Python-based software. Because there might be possibilities that the Pythons actually cannot, in this very narrow scale, like 10 to the negative 16 or 10 or 11. So it's actually, we assume that actually even before 10 to the negative 9.5, even before here, there might be a fluctuation in here. But it's just because we zoom in more and more, so we can see that there is a fluctuations. And so we assume that maybe even before this, there might be already happening in this kind of phenomenon. And so maybe that's just simply because Python can distinguish such a small scale, so when we zoom in more, we can't really calculate the templates that we insert into Mesh View. And then we also see a significant SNR drop and observe when sample rate decreased from 4,096 to 512. It's actually not reasonable because the SNR is actually just describing the signal and noise ratio, whereas the sample rate actually is observing the highest frequency that we can detect. And so that might be a problem with the PSD, or it might be a problem with the templates. So I think these two problems are something that we have to consider and then to figure out. Because it should be, even I change the sample rate to 512, the SI should not be influenced too much. The sample rate should not influence the SI too much. But it seems like I run all the process, this process, even or the previous process, even using so these are the sample rate fixed as 4096. But I also run the 512. But I see that there's a significant drop. The same sample rate, the same coordinates, the drop in the SI varies in larger to the 1,000. So I think that might be the biggest issues of that. So that's something that I have to address. Other than that, I think this is basically my overview of my for the 2 months. Start from the beginning to know about what's going on of dark matter, gravitational wave, have no pure understanding of these things. Then later on, apply those programming skills into analyzing those data, understanding those data. And now I'm facing more problems, and later on maybe I have to figure out how to solve these problems and find a solution. But other than that, I think I'm really grateful and I learned so much. And I hope I continue to, I don't know if I'll focus on this project, but I think I'll continue to learn more about more fascinating phenomena about dark matter and gravitation related topics. So thank you so much.
Thank you, Ron. But still, you still have to discuss. First of all, we appreciate you take everything very seriously, and then in general, you get the framework. Yes, but still something that is not close to you. I think that is common to many of you. So go back now. Usually, I find that for me, even a student, it's easier to write programs. Python, you do it better than I. But to turn it into a useful tool to learn about solving problems. So this is the skill. This is the skill of research. The skill of research is not to write program. Yeah. Now, so and then one of the things which are quite, especially probably now in this generation of so it is now all the computing is cheap, so you can print out things like this. But if computing is expensive, if you use it in the paper, it's a paper company. Nobody will do this. And it is absolute. Computer is cheap, but it is dumb, it is stupid, so you can instruct it to do it. But actually, so what is the problem? The problem is from 0 to 4,000, you want to turn it into what is optimal bin. So which means a natural scale. The natural scale of the answer would be what? I have 4,000 numbers. I want to cut it into many pieces. Right. So a natural scale is, and realistically, I can turn it into 4,000, maybe becomes 400, 40. So the scale is around 10 to 100. So this is my answer. Before I do computing. So this absolutely, now, you don't have to pay a single cent. But it wastes electricity and makes the world warmer by studying all this 10 to minus 25. You know what is meant by 10 to minus 25?
That's very.
What is that?
10 to the negative 25?
Yeah, what does it mean? 10 to minus 1 e minus 10 0.2501. And then you have 4,000 units. You want to cut it into so fine things.
That's impossible.
Right. It's a poor computer. So the computer is stupid. It's another proof they're not human. The computer is stupid. It spends its time doing this. So first, I think that the natural the answer must be 10 to 100. So we focus on whether it's 10, 20, 30, 40, 50.
Right.
Rather than 1 and then 10 to minus 25. Okay. And now you can see that from the answer. What is the difference between this? So when you say it wobbles or like printing, that is a computer's job.
Right.
It's free of charge, it is student, so I don't care. But you, as a human being, actually look at this data and try to make story out of it. Now that is your waste of your time. Right. What is the difference between this? It is constant.
Right.
After the third digit, if the number is the same, it is constant. Right. And you try to make story out of this. That wobbles, that jumps around, and that is a steadily rising. So be careful that when you watch TV, a lot of people do this. Yes. Yes, right. First of all, you know roughly where the answer is. And then you know, because all this SNR is not, it's a measurement from some data.
Right.
There's some error.
Right.
So maybe 1%, 0.1%.
Right.
What does it mean by 1%?
So it's very
1% is very small.
Right.
That means that up to the third number is not reliable.
Oh, I see.
1% is the fourth number. And then you try to make up story that this number is different from this. When 10 numbers is the same.
Oh, I see.
Right?
Yeah,
Computer
yeah.
figuring it out is computer being stupid.
Right.
The human being trying to make story out of it. Alright. So
Yeah.
this is the thing that one has to learn. Right? It's totally irrelevant. Right?
I think, yeah,